In this section, we'll talk about Riemann sums, which will lead us to definite integrals. The sums that we defined in the previous sections are examples of Riemann sum, and they're named after the mathematician that developed them. Basically, a Riemann sum looks kind of like this, where you're summing over some index f of some value times delta x. Now, I'm not going to show you the following, so just believe it's true, okay? In the previous example, we subdivided the x-axis into subintervals of equal length. It turns out that the subintervals can be varying lengths. What is important is that it doesn't matter what lengths you make each subinterval as long as n goes to infinity, because as long as n approaches infinity, the result of the sum will be, well, actually the limit of the sum will be the same regardless of whether you use regular, which is equal subintervals, or irregular, unequal subintervals. You can view an example pretty much in any calculus text of this. Okay, so to define a Riemann sum, basically what we need is we need to partition our interval from A to B into subintervals. So we can divide, start on the left-hand endpoint with A, which is the same as x naught, and then divide it into n subintervals where you go A is less than x1 is less than x2 is less than so forth, x of n minus 1, which is just the point right behind x of n, and then x of n is actually the same as b. So it gets a little bit confusing when you start saying, well, a is x naught and b is xn, and then you talk about the points in between. But you know, that's the convention that's used. Now delta x, actually delta x of I would be the width of the ith subinterval. Now remember, if you're using regular partitions, then this width will be the same for each subinterval. But if you use irregular partitions, then of course this just represents the width of each particular partition. So, and then c sub I can be any point in that ith subinterval. So c is basically any point in the interval, the ith subinterval. And the ith subinterval is from x sub I minus 1 to xi. Okay, then this sum, and I just gave you an example of this. This sum actually is a Riemann sum. And the way you state it is, it's called a Riemann sum of the function f for the partition delta. And this definition takes us to the definition of the definite integral. It turns out that a definite integral is simply the limit of a Riemann sum as n goes to infinity. Now I need to define this. It's not an absolute value, it's actually called the norm of a partition. Well, the norm of a partition represents the largest subinterval. So if you have an irregular partition over an interval, then you know you've got subintervals of different widths. But we're going to assume that this is just going to be the width or the width of the largest subinterval. So if the largest subinterval's width approaches 0, well, if that's the largest subinterval, then all the other subintervals have to approach 0 as well. So from this and what we previously discussed, we can now define a definite integral. If f is defined on the closed interval from a to b, and the limit of the Riemann sum over a partition delta, and this limit exists, then f is said to be integrable on the interval from a to b, and the limit is defined as the limit of the Riemann sum as that norm goes to 0. And the limit of that Riemann sum as that norm goes to 0 actually leads us to the definite integral. So a couple things about this definite integral. This function f of x is the same as this function here. The dx is basically for the delta xi, and you can't really determine what a and b is from here. You kind of have to know the interval. So the interval that you're actually partitioning on from a to b, then that is your limits of integration. It's what we call the limits of integration from a to b. And this limit is actually called the definite integral of f from x equal a to x equal b. The number a is the lower limit of the integral, and b is the upper limit, which you can see here. B is the upper limit. We got a couple more examples before we can deliver to you the holy grail of calculus, but we'll get to them after a quick theorem here. Continuity does imply integrability. So basically, this just says if a function is continuous over an interval, then it can be integrated over an interval. So just keep that in mind for future reference. Now what I'm going to show you now is how to evaluate a definite integral using the definition of a definite integral. Now you might remember when we talked about derivatives, we had a definition of a derivative which was the limit of a difference quotient, and then later we learned some nice rules for finding derivatives. Well, we have a similar thing here. First we have a definition of the definite integral, which is the limit as the norm goes to 0 of this sum, of this Riemann sum, which is actually the same as the limit as n goes to infinity of the Riemann sum, because if the norm goes to 0, then the number of subintervals must go to infinity. So let's evaluate this definite integral using this limit up here. Okay, so basically I'm evaluating the definite integral from -1 to 2, and the function is simply the function 5x. So we know f of x is 5x, we know a is -1, we know b is 2. So delta x, or the delta xi, is 2 minus -1, which is 3 times 1 over n. So we're going to have, or which is 3 over n. Okay, I'm sorry, I said that wrong. So that's going to be 3 over n. Remember, delta x is b minus a over n. So 2 minus -1 over n would be 3 over n. And then let's find an expression that represents a plus I delta x. Well, a is -1, so we would have -1 plus I delta x. Well, we know delta x, I'm going to say delta x instead of delta x of I, even though technically it's delta x of I, but delta x. So now I times delta x is equal to -1, that's the a, plus 3 over n times I. So that's that. Now we have all of the pieces. Now we can change this integral, we can change the integral to this limit. So we have the limit of the norm of this. Well, remember, as the norm goes to 0, n goes to infinity, so I can write it like that. Okay, so let's take this one step at a time. So I'm just going to copy everything down, but for c sub I, I'm going to put in this value. This value is what I'm going to put in for the c sub I. I'm going to use that component. So I'm going to replace c sub I with this. And then the delta x is just going to be 3 over n. Now, if you evaluate the function, remember the function is 5x. So if you evaluate the function at this, you're going to get 5 times this expression here, times 3 over n. Well, I just went ahead and multiplied 5 times 3 and got 15 over n here, and just left it on the outside. And then when you distribute the 15 over n through, you get minus 15 over n plus 45 I over n squared in here. And now we need to sum this as I goes from 1 to n. Well, I know this sum can be broken up into two terms, so we'll sum 15 over n and we'll sum 45I over n squared. I left the indexes off just to kind of make it easier to write. Okay, now, but we know we're going from 1 to n. So now I can factor the 1 over n out of this sum, and I can factor the 45 out of this sum. Actually, I could have factored the 45 out of n squared out, I guess. But anyway, we know the sum of this is minus 15n. So we're going to have minus 15n for that. And we know that the sum of I is n times n plus 1. So we have 45 times n plus 1 all over 2n squared. And then when we multiply this together, the n's cancel and I get minus 15. And then this is just going to be 45n plus 45 over 2n. I canceled the n, one of the n's up here, and that's how I got in. And then the limit of this is simply going to be 45 over 2, because the degree of the top and the degree of the bottom is the same. So that's just going to be 45 over 2. So I get minus 15 plus 45 over 2. Well, that'd be minus 30 over 2 plus 45 over 2, which is 15 halves. Now, you're going to hate me when I show you the fundamental theorem of calculus, how we can do this, evaluate this integral much differently, but you do need to see the connection between the integral and the Riemann sums. Now, here's a practice problem that you can try. Basically, just follow the same steps that I followed here. The only difference is your function changed. Instead of 5x, it's 3x. And the answer you should get should be 4.5. And if you want to go to a more complicated function, go ahead and try x squared from 1 to 2. And let me go ahead and set that up for you. Okay, so at least I'll set this up for you, and then you can do that. And then after I do that, I'll move on to the next video. So delta x is just 2 minus 1 over n. So that's just going to be 1 over n. And then a plus I delta x would be the lower bound here, 1. So it'd be 1 plus I delta x. Well, delta x is 1 over n, so I times 1 over n is just I over n. So 1 plus I over n is a plus delta x. And so that's what we're going to use for our c value. So we're going to have this limit as n goes to infinity of this sum from 1 to n of f of this, 1 plus I over n, and then times delta x, which is 1 over n. Okay, now I went ahead and went one more step here. Remember, you're given the function here to be x squared. So when we calculate this function at 1 plus I over n, you basically get 1 plus I over n quantity squared times 1 over n. So the idea there, from there now, is go ahead and square this, then multiply by 1 over n, and then use those properties for sums to try to simplify this. And then it should simplify into some sort of expression such that when you take the limit as n goes to infinity, you should be able to evaluate that limit. And ultimately, if you do the right steps, you're going to get 7/3 for the answer. And so that's pretty much it on this video, and I'll do some more examples on the next